Good morning, everyone. Let's jump to the other end of the spectrum of size of things now with an open source project. So what I'll be talking about is a way to look at mesoscopic samples, typically fixed and cleared samples, and techniques which we back in 2011, 2012 started implementing here at the Institute, namely light sheet and optical tomography. So light sheet, I don't need to explain to, I believe, most of you how it works. Light sheet has become almost the bread and butter in many labs these days. With light sheet, basically you have a single plane illumination and you inherently have three-dimensional imaging. There are other ways of obtaining optical sections. The samples using confocal microscopy. You can deconvolve your wide field images, but there's another trick you can actually do to obtain three-dimensional images from microscopic and mesoscopic samples, which is to actually obtain the whole wide field image of the whole sample, rotate it from multiple angles, and then compute the slices afterwards. It's just called computed tomography. It's a technique used by medical X-ray CT scanners. And this is basically where I'm going to be focusing the talk today and explain a little bit what we've done to bring this technology to open source format. So the project started, as I said, over a decade ago. We back then were working at the same time as the Tomanchak group on an open project, and then we figured out that we were working at the same time, so we decided to change ours to open spin microscopy, which now in retrospect was not a very good idea because the name was too close to the open spin project, which became much more well known of. But the spin on the open spin microscopy had a second intent. It was to emphasize the fact that we were focusing on getting a high precision rotation of the sample, which was for us very important to be able to do optical tomography on the same setup. So that's where the open spin microscopy platform name came on. Pavel Tomanchak, who was working on this before we were actually, so he was a gentleman and we decided to publish back in 2013. And going back to what Johannes just said, making sure you have a large enough community, that you gather a large enough community and resources to keep the project running is extremely important. And in that respect, Pavel did a better job than us. I'm sure you guys are all very well aware of the OpenSpin project. They just very recently published a paper where they've updated to Micromanager version 2, which has been one of the greatest hassles that we've had with our project, both for the OPenT and for the OpenSpin microscopy platform. Now, Emilio Gualda continue working on this and try to obviate the problems of having to be stuck with the older versions of the Micromanager for running the setup. We started doing development in LabVIEW as well. And I would invite you to follow up his work. He's just published a few months ago this beautiful rendering of several flavors of light sheet microscopy, of a do-it-yourself setup. As I said, the biggest limitation now is figuring out the resources to go back and rewrite code and readapt everything to Micromanager 2, which we have not been able to maintain, but the OpenSpin project has been, and I invite you guys to follow this. Now, on the other end of sizes of things that you can do with light sheet microscopy, you have the Mesospin project as well. I invite you guys to look into this. Now, building in Mesospin is really interesting. You get an amazing scientific grade imaging machine. It does require a lot of investment of time and money. It is relatively expensive to build one of these mesospins. The results are well worth it. It's amazing. However, if you have very limited resources and time to build a machine and you do need meso imaging, I strongly recommend that you look into optical projection tomography, because light sheet has been so important the last few years. You know, optical tomography is kind of forgotten along the way. Optical tomography is basically, as I mentioned previously, a visible light version of the X-ray CT. You render sample transparent by clearing the tissue, and then you rotate it in front of the camera by using fluorescence, for example. And then you back projection reconstruct it, and you get these optical slices. It used to take a long time. These days it's actually quite fast to do this. And I'll argue that in some cases it's faster than actually implementing a light sheet workflow. Now, an OPenT is basically a spin-off of our original open spin microscopy project, where you can build just an OPT scanner We've even done the software. You can run it on an Arduino Sketch, or you can run it on an old version Micromanager plugin, which we can make available online. The instructions on how to build it are here. It's relatively easy, it's relatively easy to build it. You basically need an LED if you want to do fluorescence, a light bulb if you want to do transmitted OPT, a stepper motor with high precision, with micro-stepping, a small micro inspection lens, and a camera. It can be a very cheap camera. You don't necessarily need to do fluorescence. Now, another interesting thing about mesoscopy is that very often you don't want to magnify, you actually want to demagnify, and that's where OPT, in my opinion, still excels. In things that are fairly large, in the centimeter range, that's where you very often will find better results, and you get quicker to good results with OPT than you get with even like a mesospin setup kind of system. Another advantage of OPT compared to SPIM is the fact that you can inherently do transmitted light. You don't need fluorescence. You don't need specimens that are fluorescent. You can do autofluorescence, but if you don't want to resort to fluorescence, you can make a very simple, with a desk lamp version, an OPT, and you still get high quality three-dimensional renderings. This is a three-dimensional rendering actually obtained from this transmitted light version of this rabbit embryo. So this is another example, something that is typically more relevant to research, a mouse pup. This is an E18 mouse pup. We can do in our cuvette up to 4, and even we've done up to 10 centimeters. And this just portrays the kind of quality you can get from an optical tomography setup. From introducing the sample in the setup until you get this final reconstruction, it takes you less than an hour today with the computer today. So I'd say that you really get a good quality out of the effort that you put into not just building the machine, but actually operating it and obtaining the final result. You can make a really very cheap version of it. I have a backpack version, which I used to bring before COVID to meetings. This is actually at EMBL back in 2018, I believe. And we were just acquiring and showing how the system operates. The controls are all in here inside this little box that contains the Arduino controller. And these are just examples of samples, exotic samples that people bring to these meetings where I used to take the backpack version of the OPT to collect images. I always get these very surprising things like tomato seeds, small tomatoes, even GFP with ethyl cinnamate clearing we were able to do with this very small backpack version of it. This is an octopus, by the way. Now, Alex Lopes, working in our lab, took a challenge of making this even cheaper and easier to build. And he came up with the Lego, which is basically a Lego version, which you can actually use with this inspection camera. The lens, which is really very cheap. You can get this on eBay for 60 euros, I believe. So now Alex brought it down to about 400 euros. You can build your own OPT. And I'm not fooling you. These are actually reconstructions made of the same embryo that we took on our OPT, and the quality is actually quite amazing with this very cheap setup. So it's really, it can be research grade if you're not looking into single cell high resolution, if you're just interested in anatomy, or just a weekend project. It's an interesting project. Large samples is typically what you would want to do with optical tomography, and this just shows you examples of things. This was used to be my world record, my claim to fame, with a 10 centimeter, 9-point-something centimeter duck embryo, and then a shark. But Ali Joke actually beat me with a mouse, including the tail, which made it much larger. But I don't think it's fair to include the tail, anyways. If you've seen the Euro-BioImaging booklet this year, the report, you may have seen this image. This is actually the reconstruction that was done on our OPT in its full glory and in motion. And it shows you how you can do a whole zebrafish, an adult zebrafish, if you want to look at humor and the internal organs. So just to sum up, actually just another thing. So what I would like to emphasize is that OPT and SPIM are really not competing technologies. They're actually complementary technologies. And one of the most interesting things is actually to be able to combine them both. I believe there is one company that has been able to incorporate OPT, even though in a strange, unusual way. I can sort of say, and I don't think it's unfair to say that you still cannot buy optical projection tomography from any company. You most of the time have to build it yourself, still have to build it yourself. So that's another reason why open source is so important. But if you want to take the extra step and incorporate it in your light sheet system, you can actually do both. So in our setup, you can do low magnification OPT, and you get the reconstruction of the whole animal or sample. But then you can go in and on the light sheet, and you can get higher resolution, and you can get higher quality reconstructions. And this just gives you an example here of a mutant that we're analyzing that was generated by the Malol lab here at the IGC that has extra limbs and several deformities of internal anatomy, which you can reconstruct really high detail with light sheet microscopy, which is a little bit more difficult to get with the OPT version, but at least you don't have to reconstruct the whole animal at high resolution in order to study just the smaller details that you're interested in. And just to sum up, a very quick review of the strengths and limitations of OPT. It's very easy and cheap to build. From hundreds to 2,000-3,000 euros, you can build a scientific grade optical projection tomography with which you can get really high quality publication and analysis level of images. One of the solutions is the OPenT. I believe it's probably still the only one fully open source that you can get out there, but there are other solutions. It's typically easier not just to build, but also to operate and maintain than a light sheet setup, even if you build your own light sheet setup. It doesn't really require lasers. You can use just an LED. It doesn't require complex optics. Cheap optics is what you need. Actually, low numerical aperture optics is typically what you need. And if you're doing transmitted, you don't even need a sensitive camera. But if you do fluorescence, you can do fluorescence, autofluorescence with really cheap cameras. As I said, fluorescence and bright field are possible, so we don't require transgenics or any of these expensive samples, expensive to prepare samples. You get true isometric reconstructions. Many light sheet systems claim to do isometric reconstruction, but it's really never isometric. With OPT, you do get truly isometric reconstruction. And for anatomical studies, I need to emphasize this is extremely important. Even though it requires this computation, so you don't have the instant gratification of getting the optical slices, you need to compute the optical slices. It is quite fast using GPUs, and I would argue that it's actually faster than the time it takes you to do multi-view reconstruction, which is typically what you have to do with a multi-view setup, especially for the very large samples. Now, it isn't all just nice. There are limitations, so you typically require low numerical aperture optics, so you can get an increased depth of field, which limits your photon capture. So doing fluorescence may be a little bit of a challenge and takes a long exposure time. Still, we're talking hundreds of milliseconds at most of the times. If you don't do the reconstructions properly, if you don't pre-process your raw data, it is very artifact prone. It is a problem. And it does require these processing steps to obtain the stacks, as I said, which for some people might be a turn off. But we have recently published a chapter, just contact us and we'll send you this information that has all the code and all the information necessary just to pre-process the raw data and then to make the final reconstructions. So feel free to send me an email. And that's it. I just